Hi everyone, this is group P1 and I'm just documenting one of the designs for our LDR. So this here is the final product of our circuit that we presented in our demonstration today. And what I'm going to talk about is this tiny little component known as the LDR. The LDR was used as the input sensor, one of the input sensors for this project. And what LDR stands for is a light dependent resistor. So it means that its resistance varies in terms of the amount of light which is being experienced. Increased light intensity decreases the resistance. So this was our biggest concern in the project, other than XP, which we fully didn't implement. But this was a big concern because we had the issue of going from input voltage, which we would have received from our analog ADC pin RA0, which is connected to our PIC, and converting that into kilolux, which is what was required by the project. So we understood that in a potential divider here, so we have our 10K resistor and we have our LDR, which form a potential divider. We understand that the voltage coming in would be proportional to the resistance, and it would vary with the resistance according to the LDR equation documented in the wiki. However, we were unable to determine off the bat how to convert this into kilolux, which is basically the light intensity. A table was provided for us, well, not a table, but rather a graph was provided for us in the spec sheet showing the relationship between resistance and lux. But we were still unsure of how to use that graph and, more importantly, how to program it. So while we weren't fully able to implement this system, we did have a working design such that we were able to take our voltage, we were able to map our voltages based on the binary number that it would have received from the ADC. So we would have said that all ones, 1111, 1111, 11, I believe that's 10 ones, that would have been in the ADC, would have corresponded to 5 volts, and therefore every one increment in binary, which means that every 0, 0, 0, 0, 0, 0, 0, 0, 0, 1 increment in binary would produce a 0.048 increase in voltage. So we took the lux meter from Brian in stores and we varied our lux and measured the voltage and resistance, and we were able to create a table. This table would have corresponded to a lookup table created in assembly. And what we would have done is we would have subtracted our input value from here, from the lookup tables, and determined when the carry flag was raised. This carry flag would have indicated an overflow, which means that we would have been below the threshold. So what we did was we recorded values at 50 lux, 100 lux, 150 lux, etc. And those corresponded to a voltage. So as I said, we already knew the relationship between the voltage and the binary input value. So from this, we could have determined which range that our input would have fallen into depending on the lux. And after that, we would have converted it to our IEEE 754 format and used it for the averaging. We understand and appreciate the purpose of the floating point value as we are handling fractions, which could not have been handled otherwise using regular binary, I believe. And we appreciate its usage. The averaging which we would have found would have been done using repeated subtraction, and we would have implemented timer 1 to get 5-minute sampling time intervals. So after 12 intervals, so our counter would have counted every time 5 minutes passed and would have accepted our LDR input value. After 12 such intervals, this means that 5 by 12, which means 60 minutes have passed. meaning that it's time to calculate the average. The average would have been found to previous hour, and all voltage values would have been recorded and accumulated in one of the registers in our table, in our assembly code, sorry. So one of the issues that we would have had also, in one of the incorrect things that we would have done in our repeated subtraction, is that we used the binary value of 12 when in fact we should have used the IEEE 754 converted format for decimal 12. Another problem that we faced was in converting, so in adding two floating point numbers, we'd have needed to convert them to the same decimal place. When I say decimal place, I mean to the same exponent rather. And this was a problem determining what the exponent was, how to know if they were the same. So anyway, thank you for your time, and we look forward to our marks from the wiki. Thank you.